currently I'm working in ZISC. I mean, I'm working in zero knowledge. Zero knowledge is coming in. I mean, it's a technology that, I would say 15, 20 years ago was a very small set of people working on that, and today is quite massive, and it's a very important technology. But today what I want to talk is about kind of a new technology. I mean, it's a technology that's not available yet. I mean, it looks in today's looks like something impossible and something magical. But I want to talk about that because I want just to, this is going to be just a motivational session about obfuscation, and especially the things that enables obfuscation and what can you do if we have obfuscation, okay? Well, let's start. I mean, what's obfuscation? Obfuscation, I would say, is much, I mean, the concept at least is much simple that even has zero knowledge. I mean, obfuscation, actually we have been trying to do obfuscation since a long time, okay? Obfuscation mainly just taking a program, encrypting this program, if you want compiling this program, so you get a program, you just compile the program, you encrypt the program. And the idea is that you can run the program. I mean, you have a compiled program, I mean, an encrypted program that you can run the program. But actually, if you are trying to do reverse engineering, I mean, if you are trying to get inside what's in the program, actually you cannot learn anything, okay? Again, I mean, this is not possible today. I mean, cryptography by obfuscation is probably, no, it just don't work, okay? But this is the idea of obfuscation, okay? And actually, I want to point even something that's more important, that's more key, especially when we see the applications of obfuscation. Actually, we don't really want to encrypt the program. In most of applications, the program we want to know exactly which program we are running. What we want to encrypt is a private key. So the idea is that in this process of obfuscating, I mean, you have a program, then there is, so we generate a key, and it's a key that the program can use it, but nobody knows this key. Okay, so you can, so this is the black box of obfuscation. And okay, and why is this important? Let's see how you apply this. Okay, so I'm gonna show here about like 10 applications, just using this small box, the things that you can do. For example, one very simple thing that you can do is zero knowledge. How would you do zero knowledge if you have this key? Well, at the end, when you want to do a zero knowledge, is mainly about proving a computation, okay? So the idea is, okay, you just get a program. Actually, you run this program, okay? So this box would run the program, and just take the result, what we call the public input or the public outputs, just take the result and just sign the result of this program with the private key that's inside. Okay? Of course, this private key, you can have the public key of this key. And so verifying a zero knowledge would be just simple as verifying a signature. I mean, if this program, I mean, if this box is just executing a program, then you just verify a signature. So this, for example, it would be a huge advantage, for example, in Ethereum. In Ethereum, verifying zero knowledge, it takes 200K. With this, it would just take a normal easy recover. So very, very easy. But not only that, I mean, you can verify zero knowledge also, for example, in Bitcoin, using this without even forking that. Okay? So that's one example. Another, quite obvious, is full homomorphic encryption. How you do full homomorphic encryption? Well, actually, when you see private key, of course, you can have the public key here. Okay? So the idea is, okay, you take information, you encrypt the information with this private key, with the public key of the box, send it to the computer. The computer just runs this, but it's just running this, but this is encrypted. Okay, so what this program is doing? Well, is this program, inside the program is first decrypting the data, executing the data, and actually at the end re-encrypting the data and sending it back. So you have full homomorphic encryption just out of the box if you have this. You can have even easier what's witness encryption. Witness encryption is, we'll see some applications on that, but the idea is that you just, you encrypt the information, and if the program gets something, then you just get some output in clean, okay? Let's see some examples that you can do. For example, one is decrypt payment. Okay, so imagine that. Well, what I do is I just take some content. I mean, I can take some videos, I can take some images. Okay, encrypt them with the public key of the box, and send it there. And just share. It's an encrypted content. And the idea is, if somebody sends maybe some Bitcoin or some Ether somewhere, and then you can prove, maybe ZK verifying a block, okay, ZK verifying a chain. I mean, if you prove that you send that some coins to some address, then this program will just reveal the encryption key of the file. So they said you can put a file there, and you know that if somebody just decrypts that, then if somebody just sends some Bitcoins, then you just decrypt the file just by sending, but without any server that's running in there. Okay. DAO signing. I mean, well, it's exactly the same. I mean, this idea is this ZK verify of a chain. I mean, this is applications that are related to a chain. Right now, DAO signing, signature of a DAO is that some transactions happens there, okay? But the idea here is, okay, if I prove that something happened on chain, then, well, I can convert that to a normal signature here. So the public key of the DAO would be the public key of this signature, of this private key, and then you just prove something happens on chain, and then you just normal sign. But this signature can be CDSA, can be an RSA, or can be any signature that's based on the key. Okay, so we just can make a DAO, for example, to sign bank transactions or whatever you want to do. Bitcoin double pegging, just to make the note, is without forking Bitcoin. Well, how would you do that? Well, the idea is, I mean, double pegging means that, okay, you in the Bitcoin side, you would send some funds to a key that actually is the public key of this private key of the Bitcoin. So you would send the funds there, okay? And probably would generate some wrapping coin maybe in Ethereum. Okay, and the idea is that if I can prove with a ZK verifier that I burn some tokens in Ethereum, then this box just sign, using the private key, just sign a Bitcoin transaction for releasing the funds to somewhere else. So, I mean, if we have this, then we can have, for example, a double pegging Bitcoin. What else? Multi-party full homomorphic encryption. I mean, we want to do a computation with many. Each of you has some information, and we want to compute some information that's encrypted everywhere. I mean, it's quite obvious. You encrypt H1, encrypts his information with the private key of with the public key of the private key of this box. This box just executes whatever information, and the result, of course, encrypted with, I mean, depending on the which information have its part, it just generates. Actually, this is whatever multi-party computation, but actually you can do that in just in 2 rounds, okay, which is a huge advantage on that. Okay, voting, and probably this is more generic. Well, the idea is, I mean, is this idea of private estate. Okay, so voting is an example of private estate. Well, you can have a private estate that's a state that nobody knows, but when I'm saying nobody knows, it's like it's only this box knows. Okay, and the idea is that, well, you can do a blockchain that actually you have an encrypted transaction. Well, let me just go private state. I go here. So this you have an encrypted transaction, you have an encrypted state. Actually, you just, I mean, this box just decrypt the transaction, decrypt the state, executes, I mean, process the state, and then re-encrypt the state. And maybe just giving some outputs, can be on open or whatever it's doing. So with this you can solve this, I mean, what Aztec or some private blockchains are doing, you can solve this in a very, very natural way. I mean, and the cool thing is that you can even do that in Bitcoin, because you just need signatures on that. Related to that, I mean, at the end, voting is it's a matter of private estate. But for example, I mean, a market, an automatic market maker, or even just a normal order book market, with the order book, it's encrypted, that nobody knows about that. That's another important application that you can build if you have that. Anonymous identity. I mean, right now, for example, I mean, if you are trying, imagine that you want to organize a voting using the passports or using a normal ID. I mean, in general, the signatures are not deterministic, so you cannot use a signature as something that's unique to a passport. Okay, so the idea here is that you should be able to derive. I mean, the idea is that if you hold a passport, you should be able to derive what we call a nullifier. I mean, it's a number that does not depend, a number that it's linked to your passport. I mean, it's linked to your private key, but actually nobody can relate your private key with actually your passport. How would you do that? Well, actually, the idea is that you just do a normal verification. I mean, with the passport, you just sign something. So this box will verify that actually the passport is your passport. I would use just the private key just to generate, I mean, the hash with, I mean, the private key with maybe with your private key, and would generate this hash, and this would be signed. Okay, so you can prove that, okay, this is a number that it's related to a passport, and this number is unique for this specific thing. So you can generate this identity, but it's anonymous identity, but it's based on a basic identity. You can do it in a very natural and very simple way. Okay. I mean, there is a bunch of other applications. This is just a small set of motivating. Well, this slide was, we call it sometimes is the God computer. I mean, for political reasons, I just changed it, but because just giving the idea. But this is the idea of this. It's like having a computer that anybody can run in your, I mean, in their own place. But it's, I mean, it's a trusted computer, but it's kind of a decentralized trusted computer. I mean, a computer that anybody can run and anybody can rely on. Okay, so that's. I mean, this is just a small set of things that you can do. Things that I want to mention here. Okay, so well, I think this is. It should be, for most of you, should be enough to see the importance of this technology. Okay. So I'm going to give you some information here. I mean, this is a hard problem, okay? But actually, in the whole world right now, there is less than 10 persons working on trying to solve this tech. And I would say that of these 10, I believe that at least most of them, they are not even aware of the importance of this technology. The question is, I mean, when I ask is, well, probably there is few people because it's a challenging problem. I mean, it's a hard problem, and that's why maybe a lot of people is just don't accept that. But it should be more. I mean, it should be more people trying to work on that. I'm going to explain you now a story that just for you to realize. Okay, so there is it's a paper from, I think, from the University of Chicago, that's from people 2 years ago, something like 1 year, 2 years ago, that was something called local mixing. Local mixing, the idea was, I mean, it's a paper that comes from people that they don't used to be in the normal departments and normal research teams that they used to do cryptography. Okay, They are physicians, and they were working in a very theoretical way, but they were working more in the quantum computing related things, and one thing that was called reversible circuits that are quite used a lot in the quantum computing. That paper, if that would work, this would enable this in a very practical way. Okay, if that paper would work, then you could do this. I mean, you could execute that with a penalty of only maybe 1,000K more slower. Okay, which means that is really good. I mean, in ZK it's even worse to that. Well, this paper has been looked at a lot, and it has been proven, thanks to some grants of the Ethereum Foundation working on that, and they have been proven that it's not safe. But definitely it opens a new line of investigation of this problem. The natural way, I mean, when I'm talking with some researchers, especially the people that come from crypto, the natural way that all of them agree is that, okay, it's like things needs, I mean, the technology goes like step by step. I mean, we were in the ZK has advanced a lot. Maybe the next thing is full homomorphic encryption. And after full homomorphic encryption, maybe there is other things like witness computation, functional encryption, and then it's like at the end of the line is obfuscation. Okay? And this is probably the highway to go to this way. I mean, probably that's true. But I mean, I have the feeling, and this is a very personal thing, I have the feeling that maybe there are shortcuts. And what I'm saying that maybe there are shortcuts is that probably looking to this problem in a different ways, maybe from code theory, this comes from physics on the quantum, but there are other, if we are trying to link other research fields in different places, probably here there is something. Conceptually, the problem is quite simple, and I think that there is something. Okay, I have a couple of slides here. Just this is more some exercises. Okay, no, this is this is the idea. This is just, for example, an example that if you have one of these computers, you can have this idea of an I/O VM. So the idea is to build a tool where you can encrypt programs, okay? But the idea here is that you don't need, for this obfuscation, maybe this is a trusted setup, or you need to build something, okay? But the cool thing is that the point here is that if you are able to encrypt one single box, which would be a normal I/O VM, actually you can do it for any obfuscation things. I mean, it's just, if you build it's like the idea would be that if in electronics, if you are building a computer, you don't need to do electronics anymore. Okay? This would be the big idea. Okay? But it's like you can have like a kind of a universal circuit that just doing this single setup, then you can do it. So, and this VM, mainly how it would work, well, you will have a processor state that actually is computing from one state to the other. And the idea is that, okay, this state actually decrypts the state, executes the state, re-encrypts the state. Okay? Of course, everything is encrypted, so you don't do nothing, so you need to do something else, okay? So probably, you need to work with memory. The idea with memory is that you can have two boxes, and you can communicate these boxes. I mean, they have the private key, so they can share a public key, and they can send information on that. And you can have like another box that maybe is the memory, and this memory that, doing memory is in an obfuscated way. Here, there are things like oblivious RAM and things like that. I mean, you want to encrypt the memory too, okay? And there are techniques for doing that. And it's not only encrypting the values. I mean, you want to encrypt also the accesses and when you are doing that, okay? So you have techniques for encrypting the memory. But in the final thing, probably you will have some input and output that are clean so that you can do things on that. If you think in applications, for example, memory, I mean, for a normal VM, in these VMs, this happens a little bit about the same on ZK. For practical applications, you don't need a lot of RAM. RAM is a problem, no, but look, if you go to the 60s, 70s, or even 80s, microcontrollers, embedded devices, they used to have the order of magnitude of bytes of RAM. I'm not talking about kilobytes or megabytes or even gigabytes. I'm just talking about bytes, 64 bytes, 128 bytes, maybe 1 kilobyte. Okay? Most of the applications, you can do it with that. On that, so it's just for things. So it's not, and this VM, and if you think about all these applications that I've been talking about, okay, the program can do a lot of things, but the part that's critical is quite small. I mean, it's when you are manipulating this key is where the part that's critical, okay? So even from the practical perspective, I mean, the people that's trying to solve this in a more theoretical way, okay, it's less thinking is something quite generic and theoretical, okay? But with small things that you can do that, you can enable a lot of these applications. So it's important, this communication between the practical applications and theoretical applications. Okay? So yeah, that's very much what I wanted to think. I mean, if anybody is interested in research, I mean, there is plenty of literature in the space. I'm not a researcher, so I'm not an expert, but I mean, I've been talking with a lot of them. And my idea is just I'm trying to push as much as I can this text. So if anybody is interested in doing that, please contact me. I can put people in contact that are working on that on different fields, on different research. Okay? So that's very much what I wanted to talk about.